You've heard of ChatGPT, right? Well, that T stands for transformer. And today, we're going to get right into the heart of what makes these things tick, the self-attention mechanism. We're not just going to talk about it, we're going to visualize it, step by step, so you can really feel how it works.
Think back to chatbots from before, say 2017. They were kind of dumb, right? They just didn't make a whole lot of sense. And it's funny because at the same time, AI was getting really good at things like image recognition. So what was the deal? What makes human language so much harder for a machine to understand than a picture of a cat?
All right, so here's how we're going to break this all down. First, we'll look at the big problem with language itself. Then, we'll see how self-attention comes to the rescue. After that, we'll get into the nitty-gritty, the QKV algorithm. We'll tackle a huge blind spot it has with word order. And then finally, we'll see how you stack all this together to build the massive models we have today. So let's start with that fundamental challenge. What makes text so different from, say, the grid of pixels in a photo? Well, it all comes down to one single but really deep problem. And that problem is something called long context dependencies. It sounds complicated, but it's not. Just imagine you're reading a novel. A tiny detail mentioned in chapter 1, maybe a character's fear of spiders, could totally reframe their actions in the final chapter hundreds of pages later. Pixels in an image? They mostly care about their immediate neighbors. But words can reach across vast distances of text to connect with each other. A model has to somehow figure out this giant invisible web of relationships.
And that is where self-attention comes in. It's the tool, the mechanism, that lets the model look at an entire chunk of text and figure out for itself which words are influencing which other words. It learns to see that web of connections all on its own.
Okay, so how does this actually start? Well, you can't just feed raw text into a machine. First, you have to break it down into smaller pieces, or tokens. Then, and this is the crucial part, you turn each of those tokens into a long list of numbers. We call this an embedding vector. For all the software engineers out there, you can basically think of this as creating a unique numerical fingerprint for every single word or piece of a word.
Now, these embedding vectors aren't just a few numbers. They can be thousands of numbers long. They exist in this high-dimensional space that's, basically impossible for our brains to picture. So, to make this easier to grasp, we're going to use a simple analogy. We'll represent each vector as a single color. And the rule is simple. If two colors are similar, it means their underlying vectors are similar. It's a really neat trick to help us visualize what's going on under the hood.
So the big question is, how does the model actually use these vectors to figure out which words are related? The answer is a really elegant little algorithm that revolves around three special new vectors: the query, the key, and the value. Let's walk through this, because this is the core of it all. For every single token, every word, we create these three new vectors: Q, K, and V. Now imagine we're focusing on one specific word. We take its query vector, and we use it to scan the entire sentence. We compare it to the key vector of every other word. It's almost like a search. And when we find a strong match, a high similarity score, that score tells us how important that other word is. We then use that score as a weight to grab a piece of that other word's value vector and pull it back into our original word. That's it. That's how a word gathers up context from everything around it.
Here's another way to think about it. The query is like you typing a search into Google. It's asking, what am I looking for? The key on every other word is like the title of a web page. It's advertising. Here is the information I have. When the query finds a good key, a good match, the value is the actual content of that web page. It's the rich, useful information that gets passed along.
Okay, so this all sounds great, but there is a massive gaping hole in this whole system. Think about it. In everything we just described, comparing queries to keys, did we ever mention where the words are in the sentence? Nope. Right now, our algorithm just sees a sentence as a jumbled bag of words with no order whatsoever.
And this slide just nails why that's a disaster. A man fell overboard versus a board fell over men. These two sentences use the exact same words. A bag of words model would think they're identical, but they mean completely different and pretty dramatic things. So yeah, word order isn't just a nice to have, it's absolutely critical.
So how do we fix this? The solution is really clever. It's a mathematical hack called positional encoding. Here's what happens. Before we do any of that Q, K, V stuff, we take our original word embedding and we literally just add another vector to it. This new vector has nothing to do with the word's meaning.
Its only job is to encode information about that word's position. Is it the first word, the second, the 10th?
Now, your first thought might be, why not just count? Add a 1 for the first word, a 2 for the second, and so on. But that's too simple and doesn't really work well. The truly brilliant solution, and for the math and engineering folks watching, this is just beautiful, is to use sine waves. By using a whole bunch of sine and cosine waves with different frequencies, you create a super rich, unique positional signal for every single spot in the sequence. It allows the model to learn much more complex relative positions like, what's the word 2 places behind me, or is this an even or odd position? It's way more powerful than just counting.
Okay, so we've got our core building block, the self-attention mechanism, now with positional encoding. But one of these on its own isn't going to get you to ChatGPT. To understand the complexity of human language, you need to scale this idea up. The way real models work is by stacking these attention layers, one on top of the other, sometimes dozens of them. The output from the first layer becomes the input for the second, which feeds the third, and so on. You can think of it like an assembly line from meaning. The first few layers might figure out basic grammar, like which adjective belongs to which noun. But as you go deeper, the layers start to learn much more abstract relationships, like tracking the theme of a story or a character's motivation across entire pages of text.
And when you zoom out, that's the real magic here. The whole QKV system, it's just a flexible framework. The model isn't hard-coded with grammar rules. No one tells it that a verb needs a subject. It learns all of that by itself, simply by adjusting the little networks that create the queries, keys, and values over and over again until it gets really good at predicting the next word.
So I really hope that gives you a much better feel for what's actually going on deep inside these amazing language models. At its heart, it's a solution to that long dependency problem in text. And that makes you wonder, right? Now that we've built a machine that can learn these complex relationships in language, what's next? What other massive dependency problems, in biology, in social networks, in finance, are just waiting for a machine that knows how to pay attention?